Hello, my name is Marc Weiss, Marc Weiss Consulting. I'm the General Chair of WSTS, the workshop on synchronization and timing systems, and I'm here to talk to you about atomic clocks as primary frequency sources. This will be a very brief introduction to how atomic clocks work. I'd like you to understand three things, and I think that'll help you understand atomic clocks. First, atoms are in discrete energy levels. Secondly, energy is proportional to frequency, and a clock is a frequency device. Discrete energy levels, what is this? The change in energy from one level to another is a specific number, neither more nor less. It is a quantum of energy. The word quantum is now popular in our culture. Lots of things are called quanta or quantum. However, the energy levels in atoms, if you put the atom in a magnetic field, it breaks these levels into what are called the hyperfine structure. That's a detail I'm mentioning because you'll hear me refer to that later. Energy is proportional to frequency. Einstein discovered this relationship that a change in energy is proportional to this frequency nu, and the constant of proportionality is this so-called Planck's constant. A change in energy levels, delta E, is proportional to the frequency nu. A clock is a frequency device. Think of the day. The sun rises, the sun rises, the sun rises. This is a system that's repeating. Every morning, it's another same state. The sun rises. Time is a count of frequency states. The sun rising counts up to become the calendar. This slide shows the energy levels in the cesium atom, as well as how it splits into the hyperfine levels with increasing magnetic field. So the magnetic field is on the horizontal axis, the energy levels are in the vertical axis, and the change in energy from this 3,0 level below to the 4,0 level above, that change in energy corresponds exactly to this frequency 9.192631770 gigahertz. And the reason it's exact is because it's a definition. The second is defined as this frequency when it is in agreement with this cesium clock transition. And of course, there's a lot of caveats on that. It has to be in vacuum, not being affected by other atoms, and it has to be sufficiently far away from any gravitating objects so that the gravity field doesn't change the frequency. So there's a lot of caveats with quantum mechanical effects on atoms, but yet atomic frequency standards have been made to be much better than mechanical standards. So if an atom is in the upper state, 4,0, and absorbs a photon of exactly that frequency, it will change from the lower state to the upper state if it absorbs a photon, or drop from the upper state to the lower state if it emits a photon of exactly that frequency. The basic passive atomic clock works as follows. You get the atoms that you want to measure in some place, in some form. You depopulate one of these hyperfine levels and then radiate them with a frequency nu that approximates the transition from one level up to another level. You radiate the atoms from the lower that are in the lower level with this frequency. You measure how many atoms have changed the state. In other words, how many atoms have absorbed one of these photons, and hence the atoms go into the upper state, and you have to detect this. And then you continuously correct this frequency nu to maximize the number of atoms that are changing the state. Here's a block diagram of an atomic clock as a passive standard. There's a local oscillator, typically a quartz oscillator. The quartz oscillator has a natural resonant frequency. It's a mechanical oscillator, and there's a mechanical natural resonance for that frequency. You then synthesize from that frequency up to the frequency of transition. For example, for cesium, there's the 9,192,631,770 hertz frequency, and that goes into what is called an atomic resonator. It can be any kind of system. It's not a resonant cavity per se, though there are some. It really just needs to tune the input frequency to the atomic response, the atomic transition, and then you measure the response of the atoms as the number of atoms that have made the transition, and then continuously tune the frequency of the local oscillator so that you're maximizing the atoms making the transition. Sometimes this is called interrogating the atoms with the input frequency. You then take out from the local quartz oscillator a frequency that you then divide down or synthesize to a frequency that's useful, say 5 or 10 megahertz, and then you output the frequency, or you can divide down that frequency to be something like 1 pulse per second to count time. So commercial atomic clocks have been around for decades. The classical ones are a cesium thermal beam standard, which gives you the best long-term frequency stability, a rubidium cell standard, which can be smaller in size and lower in cost. Hydrogen maser gives you the best stability from about 1 to 10 days. That's relatively short term when you consider a long-term stability being a month or so. These are more expensive, however, at hundreds of thousands of dollars. More recently, there's this chip scale atomic clock, which is very small size and weight and power. Don't confuse the CSAC, which can be either cesium or rubidium, with either the cesium thermal beam standard or the rubidium cell. And there are new clocks under development. For example, using atoms that are cooled to within millions or thousands of a degree of absolute zero. That's the Kelvin. A microkelvin is a millionth of a degree above absolute zero. These clocks could also use transitions. That is, the transition from one level of the atom to another corresponds to a frequency that is in the spectrum of light that is visible to the human eye or near to that spectrum. There'll be details on this presented at the workshop on synchronization and timing systems that's coming up in March. But a few more details about what I mean by a cesium thermal beam standard. In that clock, the atoms are heated to a temperature to make them stream out of the oven. They're then focused into a beam, and they travel in vacuum where they are interrogated with the frequency that comes multiplied up from a quartz oscillator, but is matching this 9 billion oscillations for the clock transition. Rubidium cell standard, the atoms are contained in a glass cell, and there are other atoms called buffer gases within the cell to keep the rubidium from bouncing off the walls very often, and for other features. This is a much smaller size than the thermal beam and much lower cost. On the other hand, the hydrogen maser is an active clock. The atoms are kept in a chamber, a cell that is a resonant cavity, and it resonates at the frequency of transition of the hydrogen maser. So the atoms self-generate the frequency. It actively generates a frequency, and the frequency is captured much like an antenna for a radio, and then amplified and generated and multiplied down and locked to a quartz oscillator, and an active frequency comes out. The chip scale atomic clock, as I mentioned, can either be cesium or rubidium. It's a miniature cell. It is not a cesium beam tube nor a rubidium cell standard. It uses a very different way of interrogating the atoms using something called coherent population trapping. This allows it to be very small size and low weight and low power, very good for applications that require that. It has better performance typically than a quartz oscillator. So this plot shows timing error at 1 day in microseconds in a logarithmic scale on the vertical axis. At 1 microsecond at 1 day is 10 to the 0. 100 microseconds at 1 day is higher. 10 to the minus 2, 1/100th of a microsecond at 1 day is lower. And then the power consumption, as you see in watts on the horizontal axis, and you see that a better clock would be lower power but lower timing error, and it's hard to get the best of everything in one device. This I'm going to very quickly mention a few details on this slide. It's available for you to peruse more carefully if you want to know some information about what's the intrinsic accuracy of these devices versus stability, and some of the applications. Another slide on oscillator comparison showing price. And finally, a last slide, how long can you hold a microsecond after loss of synchronization as a function of price and technology? And generally speaking, you can see that you pay more to get better. In conclusion, classically, over decades, the commercial atomic clocks are cesium beam tubes, rubidium cells, or hydrogen masers, with more recently CSACs. These atomic clocks all stabilize an electronic oscillator with respect to an atomic resonance. The use of atoms with quantum mechanical problems is more complex, but results in better long-term stability. Revolutionary new atomic standards are in development as commercial devices. Thank you for your attention.